Morning, everybody. It's 9:30. Time to begin what is the last lecture for 2022 of the Ronald E. Hatcher Science on Saturday lecture series. I'm Andrew Zwicker. I'm the head of communications and public outreach, and I've had the pleasure of hosting this series from the first lecture to today. And I want to thank everybody who's online from not just around New Jersey and around the United States, but from around the world for joining us on this Saturday. There's so many things that you could be doing, but you chose to spend some time here with us today, learning about some of the most interesting cutting edge scientists directly from the scientists. And I'm very grateful. Before we get started, just a couple of things. As always, but I say this for anybody who's new, please make sure your microphone is muted. And we ask that you hold all of your questions to the end of the presentation, where you can either use the raise hand function, and I'll just call on you in the order that you raise your hand. You can ask the question directly to our speaker, or if you prefer, type it into the chat, and we'll try to get to as many of those as we can. We welcome your video if you choose to turn your video on, but we are recording the talks. This is, I hope, the very last time I'm showing you a photograph of bagels and donuts and coffee and hot chocolate, because in 2023, we will be gathering in the auditorium of the Plasma Physics Laboratory, actually eating bagels and donuts and drinking coffee and hot chocolate and juice. I am optimistic that life is genuinely returning back to normal, whatever normal may mean, and can't wait to see everybody next year. So since this is the last lecture, I just want to do a couple of thank yous first. It takes a lot of people to put this lecture series together. And behind the scenes is our AV crew, Harry Samutalis and Anthony Pizzo, who make sure that your Zoom links work. They make sure that the speaker can be seen and heard, records the video, puts it into our archive for those who can't see it, who can watch it later. I just want to thank both of them. Harry's on today. They alternate Saturdays, and I see Harry is on today. So thank you, Harry, and thank you to Anthony. And the person who runs the whole show, who does everything behind the scenes, is Didi Ortiz. And I can't thank her enough, because this program doesn't run, not just this year, but for year after year after year without all of her efforts. And I know she's on here somewhere. I can't see her on my screen right now. But if we could all give the three of them a virtual round of applause for just the tremendous amount of work that they do. Okay. It is my distinct pleasure to introduce Dr. Eva Kostadinova, who is an assistant professor at Auburn University's Department of Physics and has degrees from Furman University and Baylor University. I love how she described her work. Although the focus of her work is studying fundamental principles of plasma physics, she calls her research interfacial, as it lies at the intersection of multiple disciplines, including applied math, space physics, aerospace engineering, and fusion science. I just love that word interfacial, and the fact that it is bringing in all these different areas into the topics that she loves to study. And on top of that, she, besides her research, she's the chair of the Coalition of Plasma Science, a nonprofit organization which aims to foster awareness of the full range of research, development, and industry involving plasma science. So welcome to the Science on Saturday stage. As you know, we start off each of these lectures with a list of 3 questions to share with the audience. But, and they're always the same questions, so they get to know you. So the first one is, tell us, when did you first get interested in science?
Hi, Andrew. Good morning, everyone. I hope you all hear me well. And thank you for having me. This is great. So I actually, I was not always interested in science. I was one of these kids that was always considered good in literature, history, talking, presentations, writing. I was writing poetry, and everybody thought I'm going to be a lawyer. And I I was a good student, so I was okay in all the sciences and I enjoyed them, but I didn't have any preference for any one of them. And it actually ties to the next question is if it wasn't until I met my physics teacher in 10th grade, a wonderful woman named Dina Katsarova, and I'm from Bulgaria, so it's back in Bulgaria, high school. And you know what? It's not just the way she was explaining physics that was imaginative and cool. It was the person she was that I respected so much that then I asked myself, and when you're young, you should ask yourself, and not only what do you want to do, but who do you want to be as a person? And if you don't know what a good person is, you just look around and oftentimes look to your teachers and you say, oh, I like to be like that person. And she conducted herself with such a elevated something about her. And that elevated something is what I kept noticing about scientists. They have this goals and dreams, and then their life is just looks so much happier and more interesting. And I think this was a moment, 10th grade, meeting that teacher, when I said, I want to be a scientist. And she was doing physics, and I think this is what led me to physics. But eventually, and this is another lesson I learned from another teacher that I met while doing outreach, who was teaching middle school and high school here in the US, online and in person. And she was teaching biology, chemistry, and physics at the same time. And I was like, wow, how can you even do that? How can you stretch your expertise so much? And she's like, well, you know what? We just study the problems with the natural world. They don't see physics or chemistry or biology. In fact, they all require all of them. And then I thought, well, yeah, I think you're right. And if you do plasma physics, you very quickly understand that it's not plasma physics, it's plasma science and engineering and all of it, plasma STEM.
I have to ask, did you ever, after 10th grade, tell her what you have done for your career?
Yes. So in fact, when we kept in touch and we were very good friends, and every time I go back to Bulgaria, I meet with her. And when I did my PhD in 2017, she told me, maybe in 2018, when we met, she said, I was so inspired that you went and did a PhD that I went and I did a PhD as well while you were doing yours. So she did a PhD in physics education in Bulgaria, and she defended after me. And I thought, wow, like we have this amazing relationship that keeps giving, you know. So yeah.
Love that in both directions.
Yeah.
So the last question is, could you share with us a hobby, something you like to do outside of your research?
Yeah, well, so it's kind of a tricky question because I would say I don't have this option where, you know, switch off from work when you go home. I'm just really always thinking about the questions we study at work, at home, and all the time. But I gotta say, lifelong hobby has always been cooking, and cooking at the, not just, you know, at a chefy kind of level. So I just really enjoy, well, because also at the chefy kind of level, you learn about all the science of food. And it's one of my dreams, and I think I'll get to do that in Auburn. They allow, where I work, they allow you to eventually, when you're more established, to put together a class of your choice. And I really want to put a class into the science of cooking, and do this, including one big lab class, which is going to teach you life skills, but also explain the chemistry, the biology, and the physics of cooking processes. And it's remarkable because you also can study a lot of material science, because food has this unique properties that we see in smart materials. And there's so many questions related to the behavior of food that we actually don't know. So yeah, I would say, while that's a separate hobby, it will converge. I think it will converge into the science as well.
I just say that Eva's pictures of her cooking are amazing. Every time I see them, I'm like, oh my God, they look so good.
I was going to say that when you finally teach that course, if you also put it online, I think there's over 100 people ready to audit the course as soon as you put it there. So thank you.
That would be, I would like to do that.
So with that, feeling the heat, fusion plasmas used to study spacecraft heat shields by Dr. Eva Kostadinova from Auburn University. The floor is yours.
Okay. Oh, and my name of my high school in Bulgaria, it's called the Plovdiv Language School. So it's actually Plovdiv English Language School. And it's a high school in my home city where you go and you study most of your classes in English, and that was a good preparation to, then apply to study at the university in an English-speaking country. Okay, so okay, let's do this. This is one of my more recent and one of my most favorite topics because it combines, as you see, I like to put. This is just a subset of the names of the people who work with this project, just probably like the most involved one. But I just also want to point out the institutions that are, as you see on the right, we have people from US universities, from Auburn, UC San Diego. We have people from Baylor, where I graduated my PhD. I have people from General Atomics because this company really runs this tokamak I'm going to be talking about. And then we have colleagues, international colleagues from aerospace engineering, from the German Space Agency and the University of Stuttgart. So it takes a village to really study space exploration, but that's what makes it really fun. And you get to meet all these people with all of their amazing expertise. So, and this is my intro slide. I always have an intro slide just in case I don't get to ask all the questions that I want to answer. But yeah, you saw that I'm a currently assistant professor, and I have a degree from Baylor and from Furman. And I just want to highlight that, and well, another free time, pastime, fun thing to do is I really like to dress up for occasions. And on the upper right, you see me and my sister dressed as the butterfly effect. Which is an effect in chaos theory, where pretty much the phenomena is described by saying, okay, the flip of a butterfly in one part of the world can cause a hurricane in another part of the world. And it's an important question of how something very simple gets so complex that it evolves into something extremely complex. So this has always been the guiding question of all of my researches. How do we look at something really complex and decompose it into first principles, or the other way around? And how do things change as you grow in different levels of complexity? And I also put this photo. I'm actually right now, I'm in my sister's place. So if she doesn't even know she's part of the presentation. And this is in this apartment. The reason why I put this is also because the Nobel Prize in Physics was given partially for a lot of theoretical and numerical work on the science of chaos theory and how do we use that to predict weather. So I gotta say, I think we predicted the Nobel Prize with that outfit. Okay, so here's our outline. Each part of this talk is going to address some aspect of how do we study heat shields for space exploration applications. And we have to start by talking about plasmas. And if you've attended before, you've inevitably heard a lot about plasmas in this lecture series. But as a plasma physicist, I'm mandatory have to go over the plasma again. And if you're new, you're about to be learn something cool about the plasma state of matter. And then we're going to talk about the Galileo probe to Jupiter, which is the specific mission that kind of sparked our interest. And then we're going to study the heat shield, or the materials that were used for heat shields in similar conditions as the ones experienced in that mission in a tokamak, which is something first of a kind experiment, because tokamaks are machines that are designed for fusion experiments and not necessarily for heat shields. But we're going to see how that can work, and we're going to go over some cool experimental data, and then wrap it up with a few high-level takeaways. Okay, so now why plasma? Well, and you may have seen this before. So plasma is our what we call the fourth state of matter, or fourth in the sense that we normally look at the first three in school in K to 12, even oftentimes in college. You don't get to hear a lot about plasma, but in general, we know that if we keep adding energy to a solid, like an ice cube, it melts and it turns into its liquid phase, and keep adding energy, it turns into its gaseous phase. And now if we keep, typically plasmas are in the gas state, but not always. If you keep adding a lot more energy to a gas, you're going to turn it into a plasma. And you probably, if you have interest in plasma, you probably have at one point of your life owned a plasma ball or broken a plasma ball. It's almost inevitable. But this is our example, everyday toy that's is an example of plasma. And what's the essential difference between the other three states of matter and the plasma is that, as we know, the other states of matter are composed of atoms, or molecules composed of atoms, where we envision them simplistically as some positively charged nucleus and some negatively charged shell of electrons. But the important thing is that the total charge of an atom is zero, so equal amount of positive and negative charge. And this is very important because this determines how the particles in the material really interact. So atoms interact through collisions and through weaker forces, oftentimes called van der Waals forces, versus now we're going to see in the plasma. Now, if we keep adding energy, and this energy somehow shakes the atom, and that leads to the release of some of the electrons, now we're left with some more positive charge in the core than the negative charge we have in the shell, and this is what we call positively charged ion. But now, if you have and this is the process that we call ionization, basically the decomposition of an atom into ions and electrons. Then, sometimes it can be electrons leaving the atom, other times can be electrons joining the atom, so then you get negatively charged ions, so you can have more negative charge than a positive charge. But why is that important? Well, because, this kind of matter that's made of ions and electrons, now, in addition to interacting through collisions, can also interact through electric forces. Right, so positive and negative charges, they feel each other, and the more important thing is that they feel each other at long distances. So now this type of matter has a very different kind of behavior than all the other types of matter. And why do we care about that? And you may have seen this before, but again, as a plasma physicist, it's my duty to say this. Today, we recognize that 99.999% of all of the visible matter in the universe is actually in the plasma state. And this background photo is one of those Hubble telescope deep space photos, which aim to look as far as we could see deep in the universe. And every glowing object here is essentially primarily composed of plasma. And even these dots, they're not stars, those are different galaxies. So there is a ton of everything. As you can see, majority of what we can see in the universe is really in the plasma state. So therefore, if you want to study the universe in any way, let's say you do space exploration, you want to know something about the sun, or you're interested in completely, galaxies far away and completely different astrophysical objects, you inevitably have to learn about the plasma state of matter. And however, we have various examples of plasmas, and they're not always necessarily in the start. Some of them are on Earth. So on Earth, if you attended Jim Schroeder's talk about the auroras, the northern lights, you've learned that this is one example of plasma that happens in the Earth's atmosphere. And I've highly encourage you to go to Alaska, for example, and see the auroras if you have a chance to travel. it's phenomenal. And then we use the same kind of plasmas at in different kind of neon signs. So this is all plasma. And as the temperature increases and pressure increases, obviously the most famous example probably for our life is the sun is a giant object of plasma. And the core, well, even though it looks all perfect when we look at it from Earth, it looks like a perfect sphere. It's like a solid blob or an egg yolk or something like that. It's really a gas made of plasma, so plasma gas. And it's what's interesting is that we tend to say in the K-12 education that the sun is gas. I meant to say, but it's not any old gas. It is a plasma. It's a different state of matter, and this is what makes it so special. And this is what makes life possible on Earth. And in the core of the sun, what happens, the reason why it's different is that sun produces its own energy, right? And the way it produces its energy, very simplistically, is because the temperature and pressure are so high in the core of the sun. Atoms, or well, in this state of matter, those are ions, merge together, hydrogen ions merge together, and in this process that we call fusion, energy is released, and that's how the sun makes its own energy. And then, okay, well, that's all cool, but then eventually, people in the plasma community studying the sun and studying other people who study energy and in the community get together and realize, well, if this is how the sun is making its own energy, that seems to be the preferred, and how all stars in the universe make their own energy, that seems to be the most natural and preferred way to make energy in the universe, right? Think about it. I mean, there are all the other ways that a human made may be clever or useful or easier. But if you can use fusion as your energy, then you're producing your energy the same way as the sun. How cool is that? Super cool, and not very easy to do, because obviously trying to produce very high pressure and very high temperature that only happens in some object as the sun. But part of our community, the fusion scientists and engineers of our community, are working on various ways to build an artificial sun on Earth and use it to produce fusion energy. So I'm sure you've had at least one talk about fusion, so I'm not going to go super deep into that, but I have to mention it because we're actually going to use in our experiments device called a tokamak, which is traditionally designed for fusion experiments. We're just going to use it for some other purposes. Now, what's our motivation? So the motivation is, first of all, we want to explore the solar system. Why do we want to explore the solar system? And especially the gas giants, and especially Jupiter, because Jupiter is the second biggest body in the solar system. And the way, if we understand what is exactly Jupiter's composition and how it was formed, it's going to help us trace back in time how everything, all of the materials in the early solar systems got distributed everywhere in the solar system, and more specifically, how did some of the key components that enable life on Earth ended up on Earth. And we believe that Jupiter formation was key in the beginning of life on Earth. If we understand that, then that helps us tremendously to understand, okay, if you need a Jupiter, and not just a habitable, a place like Earth to be in a habitable distance from the Earth, and it has atmosphere and things. But if you also need a Jupiter in a system to get life, then that allows us to look for life more efficiently outside of Earth. So there are many other fundamental questions, but this is one big one. Origin of life essentially goes through us knowing how and why the gas giants formed. Motivated by this question was actually raised in the 60s. And it took like 10 years to negotiate that this is a big deal with the whole community and make going to Jupiter a priority mission. And finally, in So actually from the 60s to the 1989 is when it was launched. All of this process, these decades of work had to be put into this mission called the Galileo mission to Jupiter, where a spacecraft was sent to Jupiter, and part of its goal. So first of all, it took 6 years to arrive to Jupiter. So this is no small mission. This is a very big thing. And then the mission consisted by one orbiter probe, and then so one spacecraft that's orbiting and taking measurements around the planet, and it also included a probe that was injected into the atmosphere with the goal of measuring locally what is happening, what is the gas composition, what are the electromagnetic fields, what is going on really, because everything else we have is observation or kind of like flyby measuring here and there small things. But before that, there was never data on what is really actually happening inside of Jupiter. But to make it possible, this probe actually had to be injected into Jupiter's atmosphere with a speed of over 47 kilometers per second, which is 30 miles per second, which is about 100,000 miles per hour. So, let that sink. What happens to an object if it's traveling so fast through a very thick atmosphere? Well, what happens is that it starts catching on fire in a sense. So not the traditional fire, but what's happening is that when a spacecraft goes to a very thick atmosphere at very high speed, then the temperature around the spacecraft raises so much that the layer of gas surrounding it ionizes and turns into plasma. And now this plasma is very hot and very dense, and it starts destroying the spacecraft. And this is basically the same mechanism why shooting stars are glowing when they enter Earth. Same thing happens, they're actually burning. So to protect the spacecraft from this burning, burning is not very technically correct term. So the correct term is ablation. But ablation, and this is the one term that I'll keep repeating because it's the technically correct term, is really the process where a material burns in a controlled way, kind of slowly. And in this process, it takes away the heat from the rest of the object. And based on this principle, this is the principle on which most of heat shields are based on. So we covered the spacecraft. If you let me turn on the pointer. So we covered the spacecraft with some material that we've studied very well, and we know exactly how much mass it's going to lose for how much time, and we calculate how much mass of this material should be put as a heat shield of the spacecraft so that it survives a certain amount of time, which is pretty much, it's usually about on the order of a minute or so, where the spacecraft is very fast, it enters very quickly the atmosphere, and then it starts slowing down. And it slows down, everything cools off, and it can open the parachute. And I think this previous picture was showing exactly this. So it shows that slows down, opens parachute. By this point, coming from here to here, the heat shield should have ablated, and you're left with only whatever was the scientific payload. So yeah, basically, but the key for this working is you got to know your heat shield very well. However, what happened in Galileo was unprecedented. That was by far the toughest entry that has been attempted, because when the probe was entering, the temperature was raised up to 28,000 Fahrenheit. And this is a picture of what the heat shield looked like. So this black thing is the heat shield. And this is a picture of after the entry, how much of the heat shield was left. And you see there was quite a bit left on the nose. This is called the nose of the probe. And there was almost nothing around the side. So this is half of an inch. So it almost didn't make it. One reason for that is that, so first of all, 90% of all of this mass loss happened within the first 16 seconds. So you see this a very violent process of material destruction that happens. And this huge amount, so about 80 kilograms of material was almost sufficient to just survive, make the probe survive for 16 seconds. So that tells you quickly that, oh my God, like this heat shield, you got to have a lot of material if you want the spacecraft to be surviving for long periods of time, going through thicker and thicker atmosphere, which means that doesn't leave you a lot of, there is a weight limit on how much these things can weigh. So it doesn't leave you a lot of weight to put into scientific payload. So essentially the calculation was that 50% of Galileo probe was of the weight of Galileo probe was actually the heat shield, leaving only 50% for scientific payload. And that was the whole point, to get the payload to the scientific instruments to measure things in the atmosphere. So you see how this is a tricky thing, balance of the weight. The reason why this is such a violent process is that to imagine what is the heating that happens, it corresponds to 15 kilowatts per square centimeter, but that may not be may not speak to you too much as units, but this is also 1 billion joules per square meter, which is about the energy of a lightning striking. However, imagine lightning repeatedly striking an object over 16 seconds. This is the amount of heat that that the heat shield has to withstand. So, and I probably am giving so much background, and we may be running short on time, but it's just so interesting. I love talking about that. But anyways, how do we know how much we lost? Because it was dropped in the atmosphere and it disappeared. They were very clever about this design. So this is your scientific payload. This is the heat shield. And so the nose is what we call the stagnation point, kind of like the tip of the nose. And then you have these sides that we call this downstream region. So inside the heat shield, they had these probes embedded that were just little pieces of the same material that were connected to a little circuit. And as the material was getting destroyed, then the resistance in the circuit was changing, and that translates into some voltage change. Anyways, so that gives us some real-time measurements of how much mass was lost as a function of where the sensor is located along the heat shield. And now I don't have too many plots like that, but this is kind of like the reason why we needed to do something about this. So this is a plot of how much mass was lost as a function of where you are located on the shield. And as you see, this A12 is this location close to the nose, and 1 and 2 are like 2 sensors on both sides, and then 3 and 4, those are sensors further down. This squares here are the actual measured, how much mass was lost or was measured to be lost from each sensor. And these circles here are how much mass was predicted to be lost as a function of where the sensor is. And as you see, close to the nose, our predictions, the theory, numerical, and predictions from Earth experiments over-predicted how much mass will be lost, and under-predicted how much mass will be lost along the sides. And this was the really dangerous thing, because the probe almost didn't make it because of this big gap here. And honestly, the reason why this happens is that no matter what experiments were attempted in the 70s and 80s to really study this material and what's going to happen, no single experiment could reproduce the actual extreme heating conditions, the actual temperatures and pressures and densities of the plasmas that are really going to be hitting this material, until we came up with that idea to do it with a tokamak. Of course, it's a crazy idea, because tokamaks, as I said, they are machines that are designed to produce plasma as hot as the plasma of the sun, and as dense, it turns out, as the plasma that forms around a probe entering Jupiter, like Galileo. There's another convenience with tokamaks, is that they usually make plasmas out of deuterium, which is a hydrogen isotope, and they have the ability to do mixtures of gases, and gas giants like Jupiter are made of hydrogen and helium. So very convenient, that's the same kind of plasma, and it's also very hot and very dense. So what we propose to do is inject a small pellet of a material in very hot regions of plasma and watch it burn. Sounds simple, wasn't very well received initially because they don't want you to inject something that's just going to be contaminating your plasma like crazy. But we got it through, and I'm going to show you in the remainder of the, so again, we inject some pellet, that was small material, and watch how it gets destroyed in the hot plasma. And we wanted to do this on this machine that it has never been used for that particular purpose. Not that they haven't observed this kind of process, but never for heat shields. And this leads us to the D3D tokamak. Now, I'm not a fusion expert, so I'm not going to go into in length explaining to you exactly, all of the amazing research that goes on that facility, but I'm going to tell you so much. So D3D tokamak is currently the most active tokamak in the US. So most of the community that does experimental work in fusion is working on this facility right now. And there are multiple other designs that are now happening, but this is a big one. It's a medium-sized tokamak, which means that you see here the size of a person in comparison to the size of a tokamak. It's not a small machine, and still, there are bigger tokamaks in the world than this one. But what was important for us is that, so it's a machine that has a toroidal shape, which we informally call a donut shape. And if you slice it and you look at the cross section of the plasma, it's not exactly like the slice of a donut, which will be circular cross section. It has this it's called diverted plasma. So it's, in addition to the circular part, it has these two legs that are also lead some plasma down to the floor of the tokamak here. And that's turned out to be important for our experiment. But anyways, so here's the plasma here. The very important thing for us was that the walls, the inside walls of this tokamak are all carbon-based. And carbon is the material that's most typically used for the heat shields. So this machine, by its design, is very robust against carbon contamination. And I say contamination because if you want to make some hydrogen plasma, or deuterium in that case, and you put some material and you want to keep it very hot, and you put some external material, well, this external material, in the process of dissociating from molecules into atoms and then from atoms into ions, it actually sucks energy out of your plasma and cools it down, which is kind of like disrupts the conditions that the tokamak people want to achieve typically. So they don't like contamination, but they inevitably get it from their walls. And that's why they have a lot of various ways to diagnose how much carbon is there and where is it and where does it go. And they model this. So they're world-class people who are doing this, know what's going on with the carbon and a hydrogen plasma, which, however, they work in the fusion community. They don't often get to meet the people from the space community and talk. And that's why it's very important to bring these kind of projects to really connect the communities, and they realize, oh, we're studying similar problems, which is kind of cool. Now, this is a photo from the inside. This is so these carbon walls, and I really don't know what every single object is on the wall, different kind of diagnostic ports. But what we're interested in is this little hole here that's called the DIMES port. It looks tiny, it is tiny, but what you can do on it is you can put a sample of a material. So let's say some usually flat sample, but we're going to see that we also did some rods samples like protracted from the floor. You can put it in, so it can kind of get lowered and then put further up into the plasma. So you can expose some material into this location of the plasma. Why this location on the floor is important? Because again, as I said, if you slice the cross section of tokamak, it looks like a kind of like a misshapen donut, or like the letter D, this stands for one of the D's in D3D, the name, and it has these legs of the plasma that reach the floor. Now, what's important here is that if you move around these legs, you can get so the plasma around these legs is very hot, and the plasma in between the legs is not hot at all, and the plasma on the sides of the legs is kind of intermediate hot. So actually, by slightly moving the plasma on top of this DIMES location, you can change how hot the plasma is. And this, you can kind of in a controlled way, kind of increase the temperature and see what's happening with the material. So this was a huge advantage of that machine. This was our whole goal was, okay, let's just stick some materials. And it's actually two types of experiments, and we're going to see two types of experiments we can do with this DIMES port. One of them is stick some stationary material. So this is, again, this kind of head that get put into this hole, and it can be lowered and moved into the plasma. And we could modify it to put some rods made of some, in our case, graphite material. So one type of carbon-based material, and they stay stationary. Or, and we're going to see the second approach is you can actually make some little pallet launchers into the same kind of head and inject little pieces of materials deeper in the plasma. And the two approaches have different but complementary advantages. Now, the first approach, when you use a stationary sample, is the good thing. So these rods, just to imagine, they're about, our goal was, okay, let's see what happens to different shapes of different geometries of a stationary sample. Why is that important? You would notice that Galileo probe entered Jupiter with the pointy side forward, right? Like that. But if you also, and that was at the time, they thought that this is the best way to do this, with the pointy end forward. But then if you've seen some images of how astronauts come back from the space station, and they really come back in a capsule that looks very similar to that. And they really dropped, yay astronauts for the courage, but they really dropped into the atmosphere. And this capsule is also covered with a heat shield, and it survives this burning process, the ablation process, as it enters the atmosphere. But they're dropped with the blunt side forward. So you see, geometry matters. And we wanted to kind of do different shapes, and we did one that's pointy, edge forwards, and kind of orient the rods so their geometry end or like side is facing the plasma. So we had one with pointy end forward, one with blunt, so just a cylinder with the blunt side forward facing the plasma. And we had one with the concave. And that concave is not like a shape that you necessarily want in a spacecraft, but it's very interesting to explore the extremes and see what happens. We actually did discover that the concave one, it's very robust. It's not preferable for aerodynamic reasons for entries, but it did teach us something about how the plasma interacts with the material in its shape. So, and those are tiny rods, and I'm going to show you a picture of them. But they allow us to study this mass material, how the material behaves under very hot plasma. The good thing, so the big advantage of doing it this way is that you can analyze them, so you before and after. So before, we can weigh, so for every rod, we can weigh a type of rod, how much did it weigh before exposure to the plasma, and then how much did it weigh after. So we actually know a total mass lost for each rod, so that's simple enough. And then we also know, okay, how much time did we have a plasma over the rods, and we also will use, and I'm going to show you this. We also have a way of determining how much surface area, so of that facing of the rod facing side got really ablated. So then you can come up with mass lost as a function of time, as a function of surface area, and this is what was measured by the Galileo probe. So we can actually compare, what's happening in the tokamak versus what's happening when an entry happens into Jupiter, and see, are they similar? Do we achieve the same conditions? And you see, pre-exposure and post-exposure, they did lose mass. And you definitely see that this pointy one lost quite a lot of mass. So it's not like the pointy part is not there yet, is not there anymore. And this is kind of, this was what we expected. Pointy things ablate more. Then we have this, what we didn't expect is that this concave rod didn't lose as much, even though if you think about it, it has pointy sides, right? But it just has this cavity in the middle. So that's kind of a very interesting question. We think we have an explanation why this is happening, but yeah, it didn't lose as much mass. And then the central one, it lost some intermediate amount. We could see, so in real time, when we were doing the experiments, there is this top camera view that looks at the floor, and you can actually tell how much each, so if by the how much the rods are glowing, you can tell how much mass they're losing. Because what they do with these cameras, they put a filter that can only see carbon ions. So if you're producing a lot of carbon ions, the more you're producing, the more glow you see, and you don't see the glow from anything else. Like if you put a filter, you kind of filter out the plasma and anything else, and now you just see these carbons. And you see this one pointy one, which is, I turned this upside down, so they actually correspond to what we see in the camera, but this brightest one is the pointy one, and the least bright one is this concave one. So we could in real time already say, oh, I see this one is burning much more than the other one, so you have an idea. And then you can do some more detailed analysis, like if you really zoom in this image and you see this like pixel by pixel images, then from there you can actually extract from the glow, from from the brightness of each rod, you can extract like how hot the temperature was, and we obtain information from real time this way as well. And then the final step was to use this cool machine called a scanning surface scanner. So basically what it does is, so here's our, like, let's say the cylindrical rod, which we know exactly how it was engineered. And by the way, this rod design and a lot of the work for this experiment was done by undergraduate students. So don't always think that it's fancy scientists who did this. Undergraduate students in college from UCSD, they were engineers also. They did this design and measurements and manufacturing of these rods. And then you can put it under this surface scanner, and what it gives you, so this is a map where color means height. So it's kind of like if you're red color, you higher height, and then if you're blue color, you get to a lower height. And this kind of tells us like how much of the surface did we lose. You see, we obviously lost much more from like the blue region and very little off of this base of the rod. So it's not as if it was kind of uniformly losing mass from everywhere. It was losing mass definitely in some regions more than in others. And that's, again, is very important when you want to talk about geometry. And this is a bit packed with data slides, but basically what I was saying, the takeaway here is that to know how much mass was lost, we need to know what was the mass before and after. So what is the total change of mass? What was the surface area affected, which is what we get from these scanners, and for how much time? So then we get this mass lost per unit surface per unit time, and this is what we compare to the flight experiments. It's pretty cool. And we did end up seeing that we lost similar amounts of material as the Galileo probe. But the problem is that the stationary rods, they don't really reach the very, very core plasma that's very hot. So the rod experiment was really showing us, how to adjust our theoretical models, but for lower heats. So it was similar to Galileo, but at the very early steps of the entry. And then we didn't reach with that experiment the very high heat that happens during like the actual entry. And for this, we went to the other experiment where we shoot a little pellet. So this is a video, which I don't know if I can click when I'm on a laser. let's see. No, I cannot click it with a laser. So anyway, so this was a video of how this a little palette is shot, but in general it's the same kind of like dimes location where we have this dimes head, but now we drill this cavities in it, and inside of each cavity we put this like little piston with a string, with a spring. And on top of it, we put some pellets of carbon material, and then we inject it in the plasma. And now this injection, depending on what velocity, starting velocity we can pick, can take the pellet deep and deeper and deeper in the plasma to hotter and hotter regions. So this was our kind of like now tiny spacecraft prototype of like, oh, you can think of it as a tiny meteorite entering deeper into hotter and hotter plasma. So we had different kinds of pellets, and so that now we wanted to study different types of carbon. And one of them is what's called porous. Porous stands for pores, and then you see how it looks kind of fluffy. It basically is like sponge-like material, and this is the preferred material for heat shields because it's lighter. Right? So it has these holes that allows the whole heat shield to not have as much mass. And in these holes, you can also impregnate some other material of interest that may be more structurally better and have other properties that you need. Another material of interest was a glassy carbon, which you see glasses, as you may imagine, they're a little bit different than sponges. They're a bit more smooth. And these glassy carbons, though, they're much denser. So there is a limit of how much carbon ions you can deposit into the plasma before you kind of really screw it up. So if it's a spongy carbon, you can have a bigger palette because it's less dense. And if it's a glassy one, you have like a tinier one. And here's comparison of like how the glassy one compares to the spongy one. And just so you have an idea of how big these things are, they're small. So this is kind of the thickness of a hair. So they're bigger than the thickness of a hair, but they're smaller than the size of a dime. So they really, and this bit is about like 10 times bigger than that bit. So they're like this one is like a few bunches of hair. This one is like a tenth of an inch, right? So anyways, but we could see them in real time from two different cameras. So one of them is this fast camera that's this camera that sees from the top, and you can see this tiny palette that it was injected, and this bright thing is this tiny palette that's injected. And as you notice, and we're going to see a photo of this, it creates something like a mushroom shaped cloud. Like, do you see this where my laser is? It looks like a little rocket, honestly, or like little comet. And then we see this on the side, and we see this mushroom shape forming. And this was very encouraging because this is exactly the type of shape that a comet will get when it's ablating very fast. So it loses. So it's, if you think about it, if it's just stationary and just hanging in the midair in the plasma, which we can't make that happen. But if it was just stationary and then the plasma is just heating it from every side, and it's just gonna start releasing material from the sphere. The sphere is gonna release material from everywhere equally. So you're gonna end up with this just cloud, like bigger. It's just gonna look like a bigger blob, but it's still gonna be spherically symmetric. But if it's flying through something, there is naturally, you form this like front and then this tail in the back, just because of the dynamics of how we do these things. So that was very cool, that it really looked like some of the images we've seen on comets entering atmospheres. And there's something else that we discovered. So in Galileo, you may ask, one question is, why did the theory really miss the experiment? Like, what was the error in the theory? And one big error was that it neglected, it neglected the role of another process That's called spallation. I promise this is the last term that I'm going to be using, but I'm going to explain it. So spallation is a process where if now the heat is beyond some threshold, which is very high for most materials, instead of just having nicely, so the surface heating up, and then, you know, some atoms get energetic and then they leave the surface and then they ionize and like make ions and just leave. Nice atomic process. What happens is if the heats are very extreme, actually whole chunks of material can get ripped off the surface. It's a very violent process. And it was predicted that it may not be a big deal. It may be about 10% of the mass loss or maybe less. In the Galileo probe entry, but it actually was more than that. And the problem is that now, if you instead of predicting what's happening to some nice uniform surface that's kind of uniformly losing these atoms in a very controlled way, now what's happening is in the middle of this, you have like big chunks of material being ripped off, which creates holes and cavities. So this is why our cavity experiment got actually very, very interesting. But like, you know, they leave rough surface, and now rough surface is a combination of pointy things and cavities. So it does not uniformly lose mass, and it starts losing mass much more than what we predict. And this is one of the big reasons why the sides of the probe were losing so much mass. And this is an image from a paper from the 80s where they actually studied this spallation process and how it looks in a lab experiment. And you see it looks like an object losing shards of, like throwing shards of material. And this is how our glassy carbon pellets look like, that they really, like if you look at them, they were first at the beginning, they throw these shards very violently, and then whatever is left in the core, if you zoom in, it looked like a tiny rocket again. So we did see this process, which was the indication that the heat that these things were exposed to exceeded the threshold for this process. So it actually did reach the heating conditions of Galileo. Sorry, got too excited. And you can see photos of this. I'll zoomed in images of how, yeah, these shards are looking like. So that was very, very, very cool. We didn't know if we we're going to see this. We didn't even, again, this is an experiment of the first kind. So there were so many uncertainties whether this is going to work, but the conclusion was, yes, we did actually reproduce the adverse conditions that the Galileo probe was exposed. And what is the benefit is we actually use this data now to fix the theory. And this is what we're trying to working on that, but this will be our contribution to the space community. So high level takeaways. Plasmas are everywhere in the universe. So therefore, if you want to study plasma, you have to, if you want to explore the universe, you have to study plasma one way or another. There's no way around it. But lucky for you, it's very fun to do that. And then exploring the solar system, as you can see, it's kind of tough. Galileo took 3 decades to conceive, and then 6 years to get there, and then 8 years of a mission, and people are still analyzing data from the Galileo probe. And as you see, we are still fixing theories related to that mission. So it's a multi-decade. I mean, some people spend their whole careers, because this is how big this is, going to Jupiter. And if you want to go back, the biggest takeaway was, well, this one almost didn't work and would have been such a huge failure if, you know why the heat shield survived really? It's because the engineers left 50% safety margin. So actually, whatever was calculated to be needed, they said double it. But what is the downfall of that? The heat shield was half of the mass. So essentially all of that effort, and then you don't have space to put many scientific tools to really actually do the science on Jupiter, which is the whole point of the mission. So our takeaway is that if you want to go back to Jupiter, if you want to do these extremely ambitious entries, we need to optimize the materials we use for heat shields. And we demonstrated that a tokamak in the tokamak community, with all of the knowledge of how plasma interacts with materials and how very hot plasma behaves, actually has a lot of wisdom that's very useful for the space community. And in addition to providing, tokamaks being used primarily to study fusion, which can provide clean energy for the world, they can also help us optimize heat shields for spacecraft entry and enable the future of space exploration. So with this, I'd like to thank you so much for your time, and I'm happy to take any questions.
Thank you so much for just a wonderful talk, an interesting talk, and a talk exactly why our audience comes to these lectures in the first place. So if you would, please either raise your hand or put the questions into the chat, and we'll get to them as you do so. So our first question is from David Jones, and if you could unmute yourself.
Thank you very, very much. That was really, really interesting. Just as a sidelight, I used to work in the GA complex 30 years ago, and I kind of wonder where they put that instrument in that circular building, but that's neither here nor there. So, carbon has a lot of allotropes now. We're discovering that it's far beyond what we expected. We have nanotubes and all those other things. We also have some materials that are probably fairly light and contain metals, which are the maxines and the max phases. Are we generating a lot of new types of carbon to maybe dissipate heat, or what's the next phase? I think we looked at glassy and graphite.
Yeah, this is a great question. So really, we started. So this was the first round of experiment we've done, and since it was the first of its kind, we started by safe types of carbon, so not very complex. So these rods were made of graphite, and ATJ graphite is very well studied material and very commonly used in tokamaks. So the people we worked with, because their walls are made of ATJ graphite, and so we wanted to start with a simple material to see if we reproduce what's already known, so that that what you're observing, what you're modeling, agrees with something that the community has already studied. So this was very useful to have a very simple material that's well studied. Then the porous, I would say the porous and the glassy carbon were two types of carbon where we were trying to take it one step further and see, okay, how does the material density really changes the outcome of like how much mass is lost. And we saw that this porous carbon pellets, they behave more like what we want. So they do these like nice clouds, and they even though they go to very hot plasma, they don't do this shards, this spallation process, and the glassy carbon does it. But the glassy carbon survives longer. So it's kind of an interplay between material strength versus this kind of unwanted process of spallation happening. And this is where, things get interesting. So all of these materials on their own don't make a good heat shield. They're just made of the right kind of atoms. So we just studied the plasma chemistry, basically, between a hydrogen plasma, or like deuterium in this case, and a carbon-based material. We did try, so the next idea was to use silicon carbide. We did try to coat one of the rods with a thin layer of silicon carbide, but it peeled off. So when we expose it to the plasma, the silicon carbide really just got released. So our conclusion was that we either need to do a silicon carbide rod, like fully made of that material. We had colleagues who said they tried that and it exploded. So we were like, maybe instead you do silicon carbide core and then coat it with carbon. And it's a matter of like, how do you imagine the sequence of events in the heating process and in the mass loss process? But silicon carbide has been discussed both in the space community and in the tokamak community as a good material. And then if you want to go really, like I would say next level, which would be next level proposal for experiments and for analysis in projects, we've discussed nanotubes now. And I think it's just a matter of finding the right people who are in the manufacturing, because we're scientists, right? So we study very fundamental things, but we need to work with somebody who is actually producing these things, or to give us an idea of what's really possible. And so I would say we've thought about that, and that's definitely like one future direction. We just haven't gotten there yet.
What about nitrides?
Nitrides, I haven't thought about that. I think we were kind of circulating around carbon because they're more well-known atomic properties. Like if you need to look at some spectroscopy or like cross sections for material interactions and things like that, we're more familiar with carbon. But that doesn't mean that other materials are out of the question. It's just a matter of like how much is available as knowledge in atomic physics, how much in combination of properties. Like, so some things ablate really well, really the way you want them in a very controlled, slow way. But then other things, but they may not be very strong. So they may not survive other parts of the trips, like going to Jupiter or something. So it's, yeah. So I'm open to answer suggestions, because this is a very new thing. We're just, I think we spend most of our time demonstrating that this experiment gave good results, and we actually can compare to something in space. But from now, yeah, the future is trying new materials.
Thank you.
Thank you. Zishan, I see you put your question both in the chat. You had your hand raised. I wasn't sure if you want to ask it, or I can certainly read it.
Oh, twisted by my microphone. Okay.
Yeah, I was just wondering, so what is the limitation with the heat shield? So how big can you make it without there being any issues? And what are the issues that are tied in with making heat shield too thick?
Yeah, okay. So this is an excellent question. This is one reason, another reason why not any material so obviously the low dimensional carbon-based materials like graphene sheets and that, yes, twisted, and then, bilayers or nanotubes, those are super cool. And we see all the time these articles about their amazing properties, right? But then, yeah, the problem is, it's an engineering problem mostly, is that you need a big, so you got to figure out a good way to design and stack things. So I'm not aware of anybody who has the ability to make big plates of, let's say graphene. You can make flakes, things like that. Or maybe you can make, I don't know how far people have gone, because they go, like material science grows so fast. But if you can make tiles, you can make tiles. So the heat shield, let's say the shuttle, the US shuttle mission was, if you go to, I would say, Houston Space, NASA Space Center, you can see this shuttle actually, and you see it's covered by little tiles. But this creates a lot of additional problems. Anytime you need to meet two edges, then maybe additional structural problems. With the Galileo probe, what they did was they actually had one type of carbon as a cap in that nose, and then on the side they had something that they called taped wrapped carbon. So it was really like a tape and kind of wrapped around. So I think it's a very interesting engineering question of, for any given material, how can you make it big? Like, can you make and how strong, how does the material's properties change? Do they scale well with size, which we don't know for some of the newer materials?
So we have a question about one of your experiments, and then a couple of questions about fusion that I'd like to get to. Okay. So the one about your experiment is, could you just talk about how close were the various rods, concave, round, edge times from the strike point?
Yeah, I can. Yeah. So I think they were about an inch away from each other, maybe even less, maybe like, so a couple of centimeters, which is like slightly below an inch, which is a good question, because then you may ask, do they affect each other? So when they face the plasma, try to make sure if you so we could initially, we were thinking, oh, we can have a bunch of rods, but then we didn't want them to shadow each other. So in other words, one of them loses material, the next one gets it deposited on it. So then you don't measure your mass loss rate very well. So we just space them kind of like oriented one way, and plasma is coming this way. So each rod has only one plasma facing surface, and whatever they're releasing does not shadow any of the other rods. And now they don't tend to like sideways give each other material, exchange material, because the plasma flow is kind of fast, and it's really like, if you imagine just flow going through stationary samples. So we would say to the first, we could verify this because we can see from the brightness of these rods, we could extract what should be the temperature as a function of time of these rods. And then from the scanning microscopes, we can see, how much volume was lost from each one of them. And then we weigh them before and after. And then we can also measure how much extra carbon was deposited in the plasma. So we have several ways of verifying that how much material came from each one of them.
Thank you. So let's pivot to tokamaks and fusion.
Okay.
Our last couple of questions. So first one. So you called D3D, the tokamak D3D, medium size, and you said it can sustain a plasma for 4 to 5 seconds. So the question is, why is the size of the tokamak related to the time a plasma can be sustained? And is this why ITER is so large?
Well, that's a great question.
Tell people what ITER is too.
Right. Okay. So first of all, let me warn you, I am not a fusion scientist, but so if I mess something up, Arturo should jump in and just kind of save the day. So my understanding is that tokamaks are machines that hold the plasma using strong magnetic fields. And because plasma is made of charged particles, and charged particles follow magnetic field lines, you essentially make like a magnetic field bottle. And in our case, it's not just a bottle, but you kind of twist it so it makes this donut shaped trap of magnetic fields that are really holding the plasma together. And now the size expanding, so expanding the size of the tokamak allows you to make with I would say with the traditional technology to have bigger coils that produce stronger magnetic field lines. Therefore, you can hold plasma for a longer time. Now, having said that, and yes, this is one reason why, and again, I'm sure there are many other reasons, but this is one reason why ITER is bigger, because it's going to produce, stronger magnetic fields. And this is going to, so the magnetic field, there was some law or rule that the magnetic field scales with the size of the tokamak. So the bigger, the better. If you're considering the technology that was well established maybe a decade ago. Recently, there have been developments of the invention, again, a very exciting invention of material science, which is again to show how plasma is so interdisciplinary, was the invention of superconducting magnets and the ability to manufacture them large. So now, if you have this much more improved technology, so these superconducting magnets are going to revolutionize the field because they can be smaller and still produce the very high magnetic field, which now allows you to build a machine. I'm not going to call it necessarily tokamak, but any machine for fusion that's using magnetic field that for confinement of the plasma allows you to build smaller scale machine with just as big magnetic field, maybe as ITER, which is very desirable because we want to build reactors and power plants based on fusion, and it's much nicer if they're compact and you can have many of them. So that was my non-fusion scientist answer. I'm sure there are rigorous ways of speaking about that.
I'll just add to the audience. There's going to be, just look out on Thursday, St. Patrick's Day, there's going to be a big announcement out of the White House of an effort to accelerate the path to a fusion pilot plant in the United States. So you'll see headlines of that coming up Thursday. And so I think our last question is coming from Stephen Doyle.
So I know everything's kind of unknown, but how long do you think it would be estimated until they could create artificial suns?
So until they what?
Create artificial suns.
Oh, okay. And this is, so let me tell you this. You can hear different opinions about that. So I'm going to give you my opinion. Again, as a non-fission, but I've been involved in the past several years in multiple community planning processes where people discuss this, how much time it's going to take. I would say, if you ask the government, they tend to do things kind of slower, but in a more safe way, right? So if you ask the government, they're going to say 20 years. But very recently, there were several big breakthroughs in the community. So multiple machines that do fusion in different ways produced much more energy out of their process than they've ever done before. And all of a sudden, this and the third thing is, as I said, is this in the invention of these superconducting magnets, and now that all of a sudden changed the game. You don't need to. ITER is so expensive because it's so large, and it needs multiple countries to build one of a one-of-a-kind machine in the whole world. Versus now with these superconducting magnets, you can achieve similar kind of conditions, but in a much smaller machine. So that makes it feasible to just do it just by the US or just by another country. And I think all of this progress now really attracted businesses, which was, I'm not that old, so I don't know how excited businesses were always. What was the relationship between businesses and government when it comes to fusion? And it was fluctuating a little bit, but lately businesses have raised, I think, I gotta say, last time it was something like $5 billion for fusion, which is unprecedented number, I think. I think what would see, if you ask the businesses, they'll say we'll have something in 5 years. So my conclusion will be, businesses tend to always push for as fast as possible and very high risk projects, which is their strength. If it works, it's amazing. If it doesn't work, the business fails. Government's always slow, but steady and kind of, just safe. So, and I would say right now we're at the position for the first time where there's a lot of, speaking of public-private partnership. So let's take the government's wisdom and the business's craziness and money and produce some partnership, which is, for example, one example of this is the partnership between NASA and SpaceX, which resulted into this amazingly, anything SpaceX that we hear is mind-blowing, but SpaceX was originally enabled by NASA and using a lot of the wisdom of NASA scientists. So same thing. So I would say probably safe bet is 10 years, between 10 and 15 years versus, it's not 20, it's not 5, but it's coming. And again, this is just my take on things, that based on that, my reasoning, that's happening.
Thank you.
Thank you, Dr. Kostadinova. Thank you so much for this lecture. Thank you, as someone put into the chat, for being a perfect example of how you take a complex subject and explain it in a way that, we have people with so many different educational backgrounds here, make it understandable for everybody. That's the exact philosophy of Science on Saturday for all these years. So I can't thank you enough for being our speaker.
Thank you so much for having me. This was so much fun. Feel free to contact me. You can look me up on the internet, but also, contact me, email me. I love to. I can't get enough talking about these things, and I'm so grateful that you spend some of your precious weekend time to learn about these topics.
Thank you, and to everybody, be safe, be well, and we'll see you face to face in January of 2023. Can't wait to see everybody. Take care.
Bye.